Hello everyone. So in the previous lecture we discussed about the molecular interactions, and then we talked about what will be the energy of a dipole in an external field, and we talked about we ended our discussion on this section discussing what is dipole interaction, I mean giving rise to the Debye equation, what is the expression for the macroscopic polarization, and if we combine these two, how we will get the Clausius-Mosety equation. Now we will continue on this, and today we will be discussing what happens, what is the origin behind the intermolecular interactions. Now we have actually our background ready, because we already discussed what is the expression for electric dipole interacting with an external field. So the interaction potential for two charges, already you know that if I write the interaction potential as V, and if the charges are Q1 and Q2, so then the interaction potential will be Q1 Q2 by 4 pi epsilon, where epsilon is the permittivity of the medium, which will be epsilon 0 if it is in vacuum, or it will be epsilon 0 times the epsilon r, the relative permittivity, if it is in some medium, and times the r, where r is the inter charge separation distance. Now what that is already known. So this is basically between two monopoles ideally. Now the question is, if I have a monopole and if I have a dipole, how the interaction potential is going to look like. Now for that we have to know that what is the location of the monopole with respect to the dipole. Now when you talk about monopole, the usual convention is that you take the monopole to be as a positive charge, and let us now work on it. So we can actually write it as leave it as Q1 Q2. For example, suppose if Q1 Q2 are one of them is a positive charge, something like say plus E, the other one is minus E. So automatically the interaction potential will be negative, because it is Q1 times Q2, and in this case it is plus E times minus E, which will give you a minus E square. So that basically tells you the interaction potential is negative, but the system is a bound system. Similarly, now we can talk about the ion-dipole interaction. Let me use some other color for that. Ion-dipole, or more specifically you can call it as a charge-dipole interaction. So now it will depend at what orientation the charge is located with respect to the dipole. For example, suppose I have the dipole like this. We have a positive end and we have a negative end. So we have basically minus Q1 charge, and here I have a minus plus Q1 charge, and where I am going to put this third charge, which is say Q2, and we are not telling anything about the sign of the charge right now, whether it is a positive positive charge or a negative charge. We are just simply saying that it's Q1, and then we can say that suppose the Q1 or the Q2 sorry is located at a distance r from the center of this dipole and along the axis of the dipole. So suppose this is Q2, which is the new charge, its magnitude is Q2, and then already for the dipole we are using some convention where we are writing capital R notation. Here actually I will just change the notation a little bit. I am using that this is L, or L is basically the length of the dipole, and from the center of the dipole the distance of the charge of the new charge is basically small r. So this is small r, and this charge is located on the same axis as the dipolar axis. Now this is a very particular geometry, of course. Now, the question is what will be the interaction potential, that we can easily figure out. So, this charge Q2 will have interaction with either of the charges Q1 plus Q1 and minus Q1, and that will give rise to basically addition of potential. So, what I am saying is if I want to write it, suppose I have the potential as V, and then I have to first consider the interaction between Q2 and minus Q1. So, every interaction, as you know, will have a term which is 1 by 4 pi epsilon, and then the first term will be interaction between the Q2 and minus Q1. So, we will have minus Q1 Q2 divided by the distance, and in this case as you can see, the distance will be r minus L by 2, because this distance we are now talking about, this distance between the Q2 charge, which I have denoted as the red sphere, and the Q1 charge, which is basically the pink circle. So, that distance is basically r minus L by 2. It is very obvious from the geometry, and similarly there will be an interaction between this Q2, we can actually mark it. So, this is the term, first term is basically this term, and then there will be another interaction with Q2 and the plus Q1, which we are going to write, and the distance for that, as you can see, is up to here. So, this is r, the internuclear, so the distance from the charge to the center of the dipole. So, it will be additional L by 2 distance. So, the distance is r into L plus 2, and this time it is between Q2 and Q1. So, we are writing Q1 Q2 divided by r plus L by 2. So, this interaction is basically between the new charge and the positive end of the dipole, and then we can actually summarize it. So, as you can see that we can actually write it cleverly. So, I can take Q1 Q2 common. So, if I do that, I will write at Q1 Q2 by 4 pi epsilon times I will have as you can see here, we will have r minus L by 2, and then if I just make a substitution, let us say x equal to L by 2r, then we can actually take the r common also here. So, in the denominator we have 1 divided by r minus L by 2 or r plus L by 2, something like that, and that I am writing cleverly as 1 divided by r, and then we can actually write it as 1 minus L by 2r. So, this r I am taking common. So, I am writing 4 pi epsilon 0 into r divide, and then I have 1 divided by the first term is basically there was a minus, and I have 1 minus x, because x is L by 2r, and the second term I have plus 1 divided by 1 plus x. Now, we have to expand 1 plus x and 1 minus x, 1 upon 1 plus x or 1 minus x, that we already know. 1 by 1 plus x, the expansion goes like 1, there will be a minus sign, 1 minus x plus x square minus x cube, and so on. Similarly, if we had a minus sign here, so we will just replace the x with minus x. So, this will be plus, the third term will be again plus x squared, the fourth term will be again plus, something like that. So, we will get a plus series for the 1 minus x, and we will get a minus series or the odd series basically if it is for 1 plus x. So, together if we write then it will be something like this. I will have Q1 Q2 by 4 pi epsilon r times I will have, let us look carefully, I will have a minus sign here, and first term is 1 by 1 minus x. So, I will have 1 plus x square plus x cube, that way it is a series, and then the second term is the 1 by 1 plus x. So, I will have 1 minus x plus x square minus x cube plus this way. This is also another series. So, what we see here is that we will have basically from here, as you can see, that we can take the leading order term, and the leading order term, this 1 will cancel the first term. The leading order term will be minus x, which is basically minus 2x. So, what we will have is we will have a minus of x, and then we will have plus of minus x. So, overall I will have a minus sign, and it will be just multiplied by minus 2x q1 q2 by 4 pi epsilon r, and then we can actually substitute the value of x was L by 2r. So, we can just write it. So, it will be minus q1 q2, and it is L by 2r. So, 2x will be L by r, L divided by 4 pi epsilon, and then instead of r I will have r square, because it is L by r, and then we know that this q1 times L is nothing but the dipole itself, and then we can actually replace it by mu. So, this term will be nothing but minus, this will be q1, q2 into mu in divided by 4 pi epsilon r square. So, we can just write the final expression. So, what we got for the dipole or with a charge interaction, that we are getting as minus, the interaction potential is minus, we can just rewrite it. Instead of writing it as mu, I can actually write it as mu 1, because mu 1 actually denotes the dipole due to charges plus q1 and minus q1. So, I am just using the mu 1 notation for that. So, we will have overall minus mu 1 into q2 divided by 4 pi epsilon into r square. So, this will be interaction for an dipole with a charge, like we had an interaction of between the two charges. Now, we see that here we have a very specific arrangement of the test charge, which is q2 with respect to the dipole. Now, of course, if q2 is positive, the interaction will be negative, because as you can see, the physical reason for that is q2 is actually closer to the negative end on the dipole. That is why it is a favorable position. But if q2 is negative, for this geometry we will have the potential energy as positive, which means actually it will be a repulsive interaction, because in that case the q2 will be a positive charge which will be close, which will be negative charge which will be close to the negative end of the dipole, which is an unfavorable position. So, in that case actually q2 the most favorable orientation will be along the axis, but closer to the other charge, where actually the q2 should be here. So, for that position will be favorable for a charge which is minus q2. Now, we will move on, and then in the next section we are going to discuss what will be the interaction between the two dipoles, because we are basically now combining our previous ideas of the interaction between how basically the dipole interacts or the dipole interacts with the field, what are the interaction potential. Now, we are talking about basically intermolecular interaction, where actually molecules may possess permanent dipole moment, and then we are basically bringing up this idea that what will be the interactions between two permanent dipole moments. So, we have first talked about charge interaction, which is already known to you, and then what will happen with a monopole and a dipole kind of interaction, which we just described, and then we are going to discuss the most important thing, which is basically interaction between two dipoles. So we will now discuss about dipole interaction. Now, before we go to that, you remember that we often talk about something like a point dipole. Now, what is a point dipole? Point dipole means, suppose I have a dipole which is something like this, which has a dimension like this. But if you view the dipole of you are doing an experiment where actually the dimensions of the experiment are fairly large compared to the dimension of the length of the dipole, which is L, then actually the dipole will kind of appear like these two charges, the distance between the two charges will appear very small, and for an observer who is far away, or for an observer who is doing a macroscopic experiment, this dipole will appear as if the two charges are coalescing or already coalesced. So, it will the observer will think that these charges are basically on top of each other, but still there will be an effect of the dipole because it is not free charge. So, we for that actually use a term which we call as point dipole. So, that is the meaning of the word point. So, it is basically as if the dipole is behaving as a point, there is no physical length of the dipole. Now, the question is what will be the interaction between two dipoles, but again we have to consider favorable geometry, and let us consider that we have a positive end like this, and then we have a negative end of the first dipole as like this. So, this is our first dipole, where we can choose the charges as let us say plus q1. So, this is dipole 1 and minus q1, and then I am bringing the second dipole to it. Obviously, the most favorable orientation will be where actually the positive end faces the negative end of the other dipole. So, a position like this, where I have for the second dipole plus q2 and minus q2, these are the charges. And let us also consider the length of the dipoles are same, meaning this is L, this is also L. This is just for the keeping the calculation simple. And as before, let us also consider the dipole-dipole distance, which is a measure from the center of the dipole to the center of the dipole distance, is r, small r. Now, again as before, we are going to basically carry out the calculation for the interaction potential, and we know that this interaction potential now will have basically 4 terms, because that plus q1 will interact with plus q2, plus q1 interact with minus q2, and so on. So, we can actually do work out the maths one by one. So, let us all follow. So, we will have 1 by 4 pi epsilon 0, and then the first thing will be, let us say I am talking about q1 minus q1 and q2. So, the nearest neighbors. So, it will be minus q1 q2 divided by the length, and the length in this case will be as you can see, if we can do the q1 q2 kind of notation, then I have r here, and then it will have plus q1. Let us say, let us first do this interaction. Let me use a different color. So, I am first I am first calculating the plus q1 with say minus q2, which is the farthest ones. Okay. So, it will be plus q1 minus q2. So, the term will be minus q1 q2 divided by the distance, and the distance in this case, as you can see, it will be r plus this distance, which is L by 2, plus this distance. So, it will be overall r plus L. Then let us consider the second term, and second term we are considering, let us say, so this was our first term between the two charges. Now, let us consider the second term, and for the second term let us consider that I have Q1, and then also take the other one as say Q2. So, we are first calculating that potential due to plus Q1. So, I am taking this plus Q1 and asking what will be the interaction potential between this plus Q1 and this plus Q2. So, let us write it. So, in this case it will be plus Q1 plus Q2. So, I will have Q1 Q2 kind of term, and then divided by look at the distance. So, I have R here. So, this distance will be basically R itself, because this is R minus L by 2, and this is actually R plus L by 2. So, we are basically adding and subtracting L by 2 from both sides. So, this will be just R. Similarly, now we can actually work out for the interaction potential of the third term. So, this was basically our second term, where actually considered the Q1 or plus Q1 and the interaction with plus Q2. Now, let us focus on minus Q1, which is this, and say first will be plus Q2. So, that term will be, since this is a minus and plus, so I will have overall a minus sign. I will have minus Q1 Q2 divided by, now what will be the distance? As you can see, this is basically overall distance is R, and then it is basically the center to center distance, which is R, and then we have to subtract L by 2 from both sides. So, we will have basically R minus L, and this is basically this interaction, and then we are left with only one interaction, which is basically from with this charge, how it is interacting with this charge, minus Q1 and minus Q2. So, obviously, I will have a plus term, which is Q1 Q2 divided by, now let us see the distance. So, the distance will be in this case R minus L by 2 plus L by 2. So, it will be basically R, and this is interaction is between the minus Q1 and minus Q2. So, now we can actually arrange the terms, and as you can see here, it is again very straightforward calculation. But in this case we have to again we can actually take the R common, but in the denominator in this case see that it is not R plus L by 2 or R minus L by 2, it is just R. So, we can actually write it down. So, if I look at it carefully, these two terms are basically same terms. So, this is between the like ends of the dipole, like plus Q1 is interacting with plus Q2 and minus Q1 is interacting with minus Q2. So, these two terms, if I take the Q1 Q2 by R common 4 pi epsilon R, let us actually write here epsilon, because we are just considering the general medium of permittivity epsilon, and then these two terms will give me a factor which is basically factor of 2. So, we will have 2 here, and then let us work out on this term and this term. So, first the first term minus Q1 Q2 by divided by R plus L. So, if I take R common, then I will have 1 divided by 1 plus x, where x is nothing but L by R, it is not L by 2R. And similarly, for the second term Q minus Q1 Q2 divided by R minus L, we will have minus 1 divided by 1 minus x. And then you see the beauty here that in the earlier case we can actually take it to be, instead of taking 2 common or Q1 Q2 by R common, we could have taken actually the minus common, then actually this will be minus, this will be plus, this will be plus. Now, unlike the previous case, this is actually addition. In the previous case, as you can see, this was a subtraction, because there was a negative sign which is here. This is minus 1 over 1 minus x divided by 1 plus 1 by 1 plus x. So we can actually write down the series once again. It's not necessary, but I'll do it just for your convenience. So I'll have q1 q2 by 4 pi epsilon into r. I have a minus 2, and then we'll have a series for 1 plus x, and that series goes as you know, it is 1, and then I'll have minus x plus x square minus x cube by 3 like this, and it's a series. I should write in the series form, and then I have a plus 1 by 1 minus x, which is 1 plus x square plus x cube by 3, and so on. So overall, what I can see here, I'll just have a term which is just 2, and then if we want to include the effect of x, we have to include the up to third term. So basically, I am truncating the series up to here, both the series, and then what I see, this x actually gets cancelled, and I'll have basically 2 here, and then I'll have twice x square. So if I just truncate up to the second term, the x cancels, and then we'll get a 2 here. Let me write here q1 q2 by 4 pi epsilon into r, and this is an approximation we are making right now, and then I have minus 2, and then plus this one, and this one gives me 2, and these 2 will cancel, and then the x's also cancel. So I have to consider another term, which is basically plus 2x square, and this is again an approximation. So these 2 now gets cancelled, and then in the final expression I will have twice x square into q1 q2 by 4 pi epsilon r, and then I know that x is nothing but L by r, so I will just replace it. So it will be minus q1 q2 2 times x square by 4 pi epsilon r, and then I am again replacing x as L by r, so it will be twice q1 L. So x square will be L square by r square. So one L I am attaching with q1, and the other L I am attaching with q2. This will be L squared divided by 4 pi epsilon r cube, and then what we have is q1 into L, and we know that q1 into L is basically the dipole moment, or the magnitude of the dipole moment for the first dipole. Similarly, q2 into L is basically magnitude of the second dipole. So overall, what we are getting is mu1, mu2 with a negative sign, and this 2 gets cancelled with this 2 to give me 2 overall, and 2 pi epsilon r cube. So thus we got interaction potential for dipole-dipole interaction. It is basically the interaction potential between two dipoles if the dipoles are oriented in a favorable condition, where actually the positive end of one dipole faces the negative end of the other dipole. So this is one of this is the most favorable geometry. You can have actually the two dipoles which are actually have a tilt angle, but that we are not considering right now. So we'll keep the discussion simple. So the dipole-dipole interaction will be something like minus mu1 mu2 divided by 2 pi epsilon r cube. And now you can review what we have just done. So if it is between two charges, as you can see, if we write the distance between the two charges as smaller, so it will be q1 q2 by 4 pi epsilon 0 epsilon r. And then if it is between between a dipole and a charge, then we see that actually it goes as 1 over r square. And then if it is between two dipoles, actually it goes as 1 over r cube. So thus we see basically how the interactions are if I actually increase the polarity of this multipole, how the interactions are basically going to look like.